Okay, let's get started. So do we have fans of Open Telemetry in the room here today? Brilliant. People using it, it works well for you? Excellent. Okay, I'm going to do my best to trash it a little bit. So this is a talk about how we grew beyond being able to work with Open Telemetry, how the scale we grew to just made the whole thing fall over for us, and some of the lessons that we learned along the way. So yeah, I work at ClickHouse. What is ClickHouse? ClickHouse is a very fast OLAP database. It's extremely good at working your observability workloads. Why is that? So we heard in the keynote this morning, SQL is the killer here. Everyone in your business who's already a data practitioner knows how to work with SQL. The AI agents know how to work with SQL. If you're using SQL, you don't have the initial tech debt of, you've got to find people who can learn it. You look at other observability databases where you have to learn some new thing. You end up with these heroes. Everyone knows the people in the company who are really good at PromQL and can write these crazy big queries. Everyone can write SQL. There's no magic there. It is extremely fast, so every optimization in the book has been thrown at ClickHouse to make it process your queries as fast as physically possible. It is brilliant at storing huge volumes of data. So what we find is because of the insane compression that it can achieve, you can just store bottomless amounts of storage. And you can do that over different tiers as well. So you can put your data, it can live in NVMe cache for the hottest data. You can then stop down to spinning disk for slightly more warm data, and then put it on S3 for just infinite retention. And as we said, we heard about compression this morning, so ClickHouse can do 20, 30, 40 times compression, no problems really for your observability data. It is also extremely good at scaling. So you can do everything from a Docker Compose on your laptop all the way to a platform like we'll talk about today, 100 petabytes worth of data. And it's not just us saying this. We have a huge number of logos across the industry who are all picking ClickHouse for exactly this set of reasons. It is just so good at observe. So let's focus on what does our stack look like. So we are running with 100 petabytes of data stored in our observability system, which, by the way, we call Loghouse. That is spread over 500 trillion rows, or half a quadrillion events worth of data. It's just this crazy volume of data, and it's growing so quick as well. So just a year ago, we were at 20 petabytes of data, and now we're at 100 and growing even further still. And that's really where we started to see the creaks of Open Telemetry. We started building Loghouse in exactly the way that any blog will tell you about, any documentation. The whole community thinks Open Telemetry is the way to go. And it is a really good product. It achieved everything it wanted to do in making everything interoperable. So you can receive logs, metrics, and traces in any format you want. You can then process them in the exact same way for any type of data. You're not locked into any particular provider of data coming in. You can then output to any data into any platform. You're not tied. You can always move between things. It works pretty well. And this is what our stack looks like internally. So we're a Kubernetes shop. Everything at ClickHouse runs on a Kubernetes node. Kubernetes node is effectively just an EC2 instance. We're in the business of hosting ClickHouse instances, so most of what we find on our platform is deployments of ClickHouse. So this is ClickHouse pods here. We can see that. We've got a Open Telemetry collector on every single node. The job of that collector is to read the logs off var log pods, make batches of them, and then forward them over to the gateway, which is a bigger deployment of Open Telemetry. It's there for larger amounts of processing. It's doing buffering of logs as it makes the inserts into ClickHouse, and for handling that insert of the data into ClickHouse. Then from ClickHouse, we're querying that. We're querying it with HyperDX. We're querying it with Grafana. We're querying it with ClickHouse SQL, just in the client, SQL console. We get to pick and choose our platform of how we view the data as well, which is really powerful. We zoom in a little bit further, and we see that we've got one of these stacks in every single region. We're doing cross-AZ optimization, so the data stays within the same AZ. We're never paying that cross-AZ or cross-region data transfer fee. We've got a ClickHouse node in every single region, which is queryable via a distributed table from HyperDX or from Grafana. All works pretty well, except for the fact that we have this, what we call the logstacle course. And what this is the flow of data between the source and the destination. And so let me work through this a little bit. As I said, we're a ClickHouse shop. What we're trying to do is move telemetry from one ClickHouse instance, which is the source, the customer instance that's running some data, into Loghouse, which is another ClickHouse instance, which is hosting our observability system. And we've got to step the data through this logstacle course to get it from A to B. So let's start. Where do we begin? We begin with a ClickHouse server, which is running, and we want to get some data out of it. It's got the in-memory representation of that data, and it marshals it to JSON, puts it to standard out, and from there, the container runtime receives that. Container runtime takes long log lines, splits them in half, or splits them into smaller chunks so that you get partial and full log lines. It then adds the timestamp at which the container runtime observed that log line being produced by the ClickHouse process, and puts that onto disk on the node. You then have, the node is also running a background daemon, which is rotating those logs over. So you get logs 0, 1, 2, 3, 4, and then the logs get thrown away. So why is it doing that? You don't want your nodes to be ballooning full of data, and so they overflow and you use all the disk on the node. You start getting unable to claim file descriptor problems from your node. So it's throwing these logs away when it's done with them. So on the node, now we've got the Open Telemetry collector. The job of that is to read the logs off the disks, so it's tailing them. It is parsing these split log lines. It is picking out smaller batches of those and forwarding them over to the collector, or to the OTel gateway, which is the bigger version of the collector. So we've already got 2 data transforms which have happened now. We've gone from ClickHouse in memory, we've marshaled it out to JSON, we've put it on disk, and the OTel collector has picked that off disk and made it into an OTLP packet, which then gets forwarded to the gateway. The gateway, its job is then to parse that JSON, to extract things like severity, to extract some timestamps from it, to extract some details about where the pod is running in Kates, form a bigger batch of those, which is buffering in memory. It then makes the insert as a ClickHouse data part, which arrives at the final loghouse destination, gets transformed into a data part and persisted to disk. Quite a flow of information. Just going to take a breather. So what's the problem with this? It's insanely inefficient when you're doing this at scale. We are wasting so much CPU on all these repeated transformations from one format to another, when really we wanted the format that we started in. So why are we wasting all this time? We have JSON stuck in the middle, and I think of this, you've got 2 ClickHouse instances on either side, and they're communicating with this like yogurt pot on a string thing, where you've got JSON in the middle, like bringing the level of what we can express down to anything that can go in JSON rather than what we can express in the rich type system of ClickHouse on either side. And then something I didn't get to talk about is the data loss that we have from this. And this is the real killer. So I mentioned that the nodes are recycling these logs, these log files, as they fill up. It turns them from logs 1 to logs 2, 2 to 3, 3 to 4, and then it throws them away because it can't keep storing all these logs forever on the disk of the node. What you find happening is, because of all this work of transforming these logs and parsing them and making batches and forwarding them over, the OTel collector on the node in the daemon set doesn't actually get the opportunity to read those logs before they're thrown away off disk when ClickHouse is logging at its peak volume, which can be really high when you have ClickHouse running in trace logging level. And so now what you have is you have this random data loss during batches of logs, and you're trying to run an investigation, and you realize that you're just missing critical data. It's gone, you've no way of getting hold of it, and the investigation is severely handicapped by just not being able to know what happened in the system. So we thought, okay, we can't be dealing with this data loss. How are we going to fix this? The first thing we looked at is, okay, so can we just stop the collectors from failing to read all these logs in time? And we realized that we're going to need 8,000 CPU cores just to dedicate to the collector if it's going to try and actually process all these logs before they get turned over from disk, which is completely unworkable. If we try and do this, recall that we're running this as a daemon set. So this is 8,000 cores which are coming out of the budget which we can bin pack for the customer instances, which means we get much less efficient usage of our nodes. It also creates problems when we have these very big nodes, so sort of 128 core nodes that we try and put a single ClickHouse instance in. If you start needing to add more and more compute just so you can handle the logs from that instance, you can no longer schedule such a big pod on that node, and you have to start having conversations about, we need to sell smaller instances of ClickHouse so we can handle these logs. Totally unworkable, and it was a complete no-go. So it was clear that what we needed was a solution which didn't involve all of this wasted effort, all of this transformation from one format to the other. We just wanted to move data as quickly as possible from one ClickHouse instance to another instance with no transformations, no parsing, just get it across the wire. And that's what we built SysX for. So SysX stands for System Tables Exporter, and its mission is extremely simple. All it has to do is move data from one ClickHouse to another, no parsing, no transforming, as efficiently as we can. It also, I mentioned it's System Tables Exporter rather than Log Shipper. Why is that? ClickHouse has a whole bunch of formats of logging which it produces. The text log is one format, and the text log gets persisted in the system table of the text log, but it also goes to standard out of the pod. And so that arrives via the OTel pipeline in Loghouse. But we were always throwing away a whole bunch of these other sources of ClickHouse telemetry, which we wanted to keep. So we have the error log, we have the part log, the trace log, the crash log, metric log, so many other logs we were never even able to consider collecting with OTel because they weren't emitted to standard out of the pod. Whereas with SysX, if we're able to hook in just directly to system tables, we can ship that data too. And there we go, System Tables Exporter. Its job is pretty simple. We connect to a bunch of ClickHouse instances, and critically, as I mentioned, we make byte-for-byte copies of that data from the source to the destination without any transforming. And so what does that look like? We can see here a simple example. So we've got two curl commands, one piped to the other in bash, just to demonstrate that ClickHouse can handle this transfer of data without any special ClickHouse knowledge. All we're doing is on the first curl, we're making a select star from the query log. I believe it's a bit small on my screen. We're making a select star and format native. We then pass that over the wire using a Unix pipe to an insert into format native on the other side between two ClickHouse instances. So just to demonstrate how efficient this can be when ClickHouse is talking to ClickHouse directly. We're not using curl in SysX, we're using the Go ClickHouse library, which is maintained internally, but you can do the same thing with curl just to demonstrate that there's no magic happening here. So we have a few interesting problems and challenges that arrive when we start doing this. One of them is in dynamic schema generation. So I mentioned that we wanted to use the exact same schema from the source ClickHouse to the destination. And what that looks like is every time we have a different schema for a system table, which happens, for instance, like in the example here, when a ClickHouse engineer ships a new metric into the trace log. That creates a new schema for the ClickHouse system table, and we want to have an exact copy of that in Loghouse. And so what we do is when SysX connects to a ClickHouse instance and it sees, oh, we've got this pod here, it's got all of these system tables we compare. Do we already have a copy of this system table? If we do, then we can just start making the inserts. If we don't, then we create a copy of that system table based on what we observed in the source with a few disambiguation columns. So that would be like the pod name, the region it's running in, what CPU type it's on, such things like that. So now we have an interesting problem, which is that we have, as we see, we have 500 tables here for all tracking the same schema of the metric log. And what we want to do is make this feel in ClickHouse like we only have one table. And that is what the merge table engine solves for us really nicely. And so what the merge engine does, unlike the merge tree, which is the building block of storage or data storage in ClickHouse, the merge table engine's job is to allow you to select from a collection of tables which you describe with a regular expression and to make that appear as though you have one single table, even though you could always drop down and look at the individual tables directly. And so the way it works is that it's looking at your where clause for your query, finding all the tables which match that where clause, building the schema for a view which would map exactly those set of tables or the superset of the columns that they have, where it converts anything to a nullable value when it needs to, and then it presents that table to you for your query. And so we get to query against hundreds and hundreds of tables as though we just have one. This is actually useful beyond just the case of something like dynamic schema generation when you're building an observability platform on ClickHouse and you want to change the schema over time. Sometimes you want to do expensive things. You want to change the primary key of your table, for instance. If you've got a very big table, we're talking about hundreds of petabytes here, we don't want to rekey the table by reordering the data on disk. We might just create a second iteration of the table with a different primary key, and then we just use a merge table to track across both of them. So lots of things that we can do here, which are much more efficient with ClickHouse. Just to refresh on what we built here. So we went from OTel, which was a multi-step process, massive overhead, potential for data loss in our pipeline, to SysX, which is direct, very low overhead, transfer data in full fidelity. And the point I want to explain is that not many people in this room probably are trying to build systems which ship data from one ClickHouse to another. But when you have ClickHouse in your observability stack, you don't have to worry about getting stuck in with one particular form of ingestion. You can just build these direct pipelines as and when you need them. But you can also use OTel and things like that when they're also totally sufficient. You never get locked into something. Just to look at the gains of SysX as well, we can see here. So we went from shipping 2 million logs a second with OTel using 8,000 CPU cores to just needing 70 cores to ship 37 million logs a second with SysX. Just shows how efficient things are when you just put ClickHouse directly talking to ClickHouse. With enough bashing of OTel, let's talk a bit about where we do actually use OTel. We're using OTel to collect the logs from the SysX scraper itself, which generates a lot of telemetry. So what does that look like? So here is some of the data that we collect from the OTel, from the SysX scraper. So we've got a piece of data point here which tells us that we've made a push, or you could consider this to be a scrape as well. So this push tells you that we've made a scrape from the part log table for this particular instance. This is the AZ that it's running in. We've scraped 120 seconds worth of data. It took us 0.05 seconds to do, and we were 600 seconds behind real time, which happens to be the target for this scraping. We then got the exact start time that we made the scrape from, so that's start greater than equal to, and we've got the stop less than. So we've got the window exactly that we made the scrape from, and then just some information about where this log line came from. So we could obviously, this all goes through OTel, of course. We can look at this in line by line like a log series. This is not magic here. We can just see this is exactly what happened. We made this push, then we made that push, then the push after that. Okay, not very interesting. So what about charting? How are we going to start drawing graphs with this thing so we can see at a more macro scale what's going on? So you might say, okay, we're going to need to start making some metrics. Does this look like a good metric? What do we think? What's going to happen to Prometheus or a stack like that if we try to stick this metric in there? We've got the exact start time as a label. We've got the stop time. We've got the name of the pod. We've got pod IP. Perhaps people using a bit of Prometheus in production are finding this a little bit of a stressful thing to look at. So what are we going to do if we want to make this work to ingest this data into ClickHouse, or pardon me, into Prometheus to understand it? We're going to have to start doing some pre-aggregation of this. We're going to have to start removing some labels from this. What does this all start to look like? It's just data loss, right? We're throwing away important information about our telemetry just so that our database can keep up with it if we're using something like Prometheus or other time series engines. With ClickHouse, we don't have to worry about this sort of data loss with throwing away dimensions from our data. We can just use this exact log line here as what we call a wide event. And so we just pump this through the system, and we can draw any charts we want from this. For instance, we might look at it like this. Again, all just that exact same log line emitted from the OTel, or from the sysx exporter. We could look at the insert lag, which is one of the dimensions on that piece of telemetry that we produced. And we can look at this over time, and we can see what's going on. So we're roughly sitting at 10 minutes, and then every now and then the insert lag is jumping up a little bit. So we can see the story that's going on here is that we're getting a little bit behind. That lag, of course, being how close to real time are we making these scrapes. And you can see it's jumping up a little bit. Something is obviously stopping the scraper. It's then catching that lag and bringing it back down to the desired amount. So we can see perhaps the scraper is crashing here or is being paused. We could look at it another way here, so we can graph those exact events one by one, put them in a sort of timeline like this, and see that we're being scraping, pause for a bit, scraping again. We can also then look at not just on the wall clock time of when the scrapes were happening, but we could look at if we look at the start greater than equal to or stop less than in series, one back to back, we can draw this chart of how much data have we completely scraped here, all again coming from the same exact metric. So great, we can look at this for a single instance and look at the lag. We can also step a level up from this and look at every single instance in the cluster and see what's going on. You can see the same sort of stories come about. We can see that we've got these scrapes happening down from 6 hours at roughly the same sort of gradient, but we've got this like one purple one in the middle, which is going a bit slower. The point here is that we can always jump all the way back to this line-by-line thing. None of the data was ever lost. We didn't throw away our telemetry when we were working with ClickHouse here. It's just being summarized at a higher level. We're aggregating at query time rather than at insert time. The other thing we get to do is to say that nothing in, perhaps we're using some observability front-end like Grafana, nothing in that we're not tied to it. If we find that we can't express the data that we wanted or the chart that we wanted in Grafana, we can just take our problems and use any tool from the data science world, right? We can just put this, for instance, in Plotly, and we can make a small little Python script which makes a graph and shows the data like that. Again, all the exact same log line that we produce. This is all just different views upon it, which ClickHouse can produce for us. So in this version of the events, we can look at the scrape time on the x-axis and the wall clock time in the y, and see that you get these anomalous patterns appearing when we're making these duplicate scrapes. And those are all driven off looking at the start greater than equal to or the stop less than. So we've just got so much power with ClickHouse to log in one format and then just bounce between any way of looking upon it that we like without having to go back and re-instrument the application with different sets of metrics. Here's another one, for instance, just another view upon the same data. We can look at some violin charts here to understand the cost of each scrape. Yeah, how is this different from traditional metrics that we might be doing with an old traditional time series database? With traditional metrics, we have to predefine all of these aggregations, right? When we get into an incident in the post-mortem, we'll say, oh, we could really do with a metric for that particular piece of information. We're missing this data. Let's re-instrument the application. Let's make a release, ship this code, and then hopefully by the time the next incident comes around, we'll have the data that we wanted during this incident. Whereas with ClickHouse, we have the full fidelity. We never threw any information away about what our application was doing. And we can ask any question we want at incident time just by producing a new view upon the same data. And the power we get from that is that we have the full platform of data science tools to just pull out any time we need them, because we just have a fantastic SQL database powering our observability rather than a traditional observability vendor. So thanks for your time. This talk is an abbreviated version of the blog post here, which is a QR code if you're interested to hear a little bit more about ClickHouse and observability. Thank you. Yeah, sure.
Does SysX do anything with the built-in OTel span table?
No.
Thank you for that, Rory. You wouldn't go back 2 slides for me, please?
Yep. This one? Another one?
Yeah. No, the one you had, the 2 of those there. I had a really good question I was going to ask you about that, but because you jumped past it, it's gone out of my head.
Apologies.
So, are you doing an additional step with transformation, or am I misunderstanding something with that SysX? Is there an additional step of transformation with the telemetry that's coming from Open Telemetry?
No, not at all. So SysX is the system which ships ClickHouse system table data. And the second piece that I was talking about was the observability about what the SysX scraper is doing and how it's collecting that telemetry using OTel.
Okay, you answered the question that I couldn't formulate there. So thank you very much for that. That's great.
Hi, great talk, thank you. I've got 2 questions. One, you mentioned the compression, right? And I think you said 20, 30, 40. I wanted to know how it compares to predefined aggregations with Prometheus or Mimir stack or something like that. If you were to just throw everything without those aggregations, does it actually end up storing more data? Or is the assumption that data is so cheap to store these days that you're just going to store everything anyway?
Yeah, the data is so cheap. I don't have exact figures for the same data stored in Prometheus or ClickHouse because we tend to store very different types of data in the two. Prometheus, you do those bucketing things into histograms or just taking like small counters where you throw away loads of labels. Whereas with something like ClickHouse and OTel, you just ship everything at it. So you end up having way more data available to you. And
Okay. All right, I lied. I guess I have 3 questions then. The Click stack, what does it look like and how does it compare to, I guess the 2 main competitors would be like the Elk stack and the Prometheus Mimir stack as well.
Sure. So the Click stack is the observability in a box version of exactly this stuff that we were talking about here. So Click stack will give you a running version or quickly to build a running version of a ClickHouse instance. It'll give you an OTel ingestion pipeline. It'll give you a HyperDX front end on top of that, all in one box with auto instrumentation of your applications. So insofar as the feature sets you get is very similar. The difference, of course, is that you get the full database behind the scenes as well. You get to have your whole SQL database rather than be limited to putting data into some observability platform. ClickStack is fully open source. It's MIT licensed, so you can run this on your own infrastructure rather than needing to pay high bills from some observability vendor, for instance. You get much better characteristics against high cardinality. If you look at something like the Elk stack, it's always a problem. Putting too much data in Elastic gets really expensive and very slow to work with. None of the problems with ClickHouse.
All right, thank you. And then last one, how would you compare to something like CockroachDB?
CockroachDB. Yeah, so CockroachDB would sit in a different space. So in my opinion, CockroachDB being a competitor to Postgres for running at very large scale, which ClickHouse is an OLAP database, so it's better for your analytical workflows, observability, BI, that sort of work. Cockroach being for more transactional work.
Okay, but the layer is actually SQL, right?
It's SQL, yeah.
Okay. All right, thank you.
Since you're copying data just from one ClickHouse table to another ClickHouse table, is there any enrichment going on? Like, how do you infer information, like on which machine is this ClickHouse instance currently running? Yeah,
sure. So what we do is we make a select. So you select star and then comma a couple of enrichment columns that you would want. And so then what happens is the source database produces that native binary with the enrichment that you wanted, which aligns with the schema at the destination.
With Prometheus, we're saying that we could drop metrics to help loading and latency. With all these additional metrics being ingested, wouldn't there be latency or lag with Prometheus when it tries to load that data, where you showed the 6 hours loading all this data?
So I didn't quite understand the question. So we weren't using any Prometheus for that example there.
That screen that you showed with all that graph, was that not Prometheus?
Oh, no, so this isn't Prometheus. So this is all based on the data inside ClickHouse. It's just doing similar tasks that you would do if you were using Prometheus. You would want to have metrics defined for all this. But the point being that we are driving all those charts off effectively log lines or events. So you just produce a log line here with a whole bunch of dimensions on it like we have on the screen. And then you can make all of these charts based just off of the data in ClickHouse.
But is it using for the front end? Is it using Prometheus?
No Prometheus at all in this. So this happens to be driven by Grafana pointed at a ClickHouse instance.
Okay, so the back end is ClickHouse and the front end is just Grafana.
Yeah, so the full stack here would be, you've got a Go binary, which is the scraper. which is emitting logs to standard out, which is these logs here, which get ingested via the OTel pipeline into a ClickHouse instance, where you make queries in SQL against it and just draw them as graphs, like this. So there's no metrics backing this. This is all just wide events.
And this can be in
It can be in Grafana, exactly. Brilliant. Thanks, guys.